Hello everyone and welcome to this training. My name is Vamsidhar Ambatipudi. As a part of this session, let's focus on trying to understand the different ways of summarizing and creating graphs or the different tabulation methods and the most common set of graphs that we give but that we get into to interpret the data. And all of you must agree to this fact that whenever we depict a graph, the purpose is to draw some kind of interpretations from that graph. So, with assuming some kind of a data is there with us, what are the different steps we would be doing to do these two activities? So, the first part I would be focusing on what are the different methods to summarize the data and what are the different common graphs that are available for us. All right. Now, the first thing we need to understand about any data is every data has 5 characteristics. For every data, I can classify the characteristics into these 5. One is the centeredness. There should be some measure which talks about the centered value of the data. Where is the value centered? What is the middle value in the data? There are various mechanisms to find out the centeredness, right? If I have to describe any data, I have to make sure that these 5 things I am comfortable with. The centeredness of it, there are many tools which we will be looking at in our later sessions. Generally, people use words like mean, median, mode, etc. But those are the different mechanisms which talk about the centeredness. So any data that comes to us, we should be able to measure the centeredness of that data. What is that central value? Along with that, we should also look at the variation in the data. Variation is dispersion. So to what extent the values are dispersing? Are they all concentrated at some around a certain value, or are they completely dispersed? What is the pattern of the data as far as the dispersion is concerned? Are they completely spread off or are they concentrated at a particular location? That is measured by variation. Again, there are different tools to measure variation, the most common one being the standard deviation. We'll come to those calculations and all at a slightly later point, but we need to have a basic understanding on any data that is given to us. Apart from understanding the context of it, or apart from understanding the sampling mechanism, etc., any data that we come across, we should be able to find out the centeredness of it, then the variation in it, then the distribution. If I try to plot the graph of all the possible values along with their frequencies, what is the kind of a shape that that graph is giving? The graph or the chart, what is the shape that it is giving? Is it a bell shape? Is it more of a straight line kind of a graph? Or is it like more skewed towards the right or the left? We'll be seeing some kind of patterns as we move along. So the third characteristic I need to look at in any data is the distribution of the data. And then the fourth one is identify the outliers in the data, which says, is there any value or a set of values which are widely deviating from the most of the other values? If most of the values are around a particular region, but this one specific value is either too high or too low compared to that particular set of other values, then we say these values which are widely away from the most of the other lot, are called as outliers. We'll have different mechanisms again to identify the outliers, but this is a simple introductory thing which talks about what are the things we need to look at whenever we talk about analysis of the data. So I need to identify the outliers in the data, and I need to know whether this data is changing over a period of time, or is it collected at one particular point in time. Because whatever the characteristics we have collected, whether it is a center or variation or outliers, over a period of time all these characteristics can keep changing. So I need to have at what point in time this data is collected, or for what period this particular data is collected. So anytime we have to do an analysis on the data, the first thing we would be focusing on is this 5-dimensional characteristics associated with this data. Right? Well, as we move along, we should be doing different mechanisms to compute or calculate these kind of aspects, which will help us in doing a proper data analysis in future. Now, the first step in summarizing the data is to build a frequency distribution. It's a simple table. The frequency distribution table is a simple table as is being shown here. Some of the things is the whole data is partitioned. The entire data is partitioned among several categories. Here you see some kind of categories are created. 60 to 69. There are 12 people. Pulse rates. A sample has been taken, and based on that sample, this kind of tabulation, if it is done. Okay, people with pulse rates lying between 60 to 69, there are 12 of them. 70 to 79, there are 14 of them, and so on. So, if I can create a table of this form, which talks about some kind of categorization of the entire data into different categories. In this case, we have 7 categories. Right? 1, 2, 3, 4, 5, 6, 7. There are 7 categories into which the entire data has been classified, and corresponding to each category, the total number of data values lying in that particular category is counted. This particular count is what we call as frequency. This entire counting is called as frequency. And definitions wise, if I have categorized this group into 60 and 60 to 69, then 60 is called as the lower limit of the class, and 69 is called as the upper limit. There is a difference between the words limit and boundary. We have to be slightly comfortable with the usage of these two words. Limit and boundary. 60 to 69, 60 is the lower limit, which could be the minimum most value that can belong to that class. 69, the maximum most value that can belong to that class. Right? But when we observe this, okay, for the next class, the lower limit is 70, the upper limit is 79. Now, what we are seeing is there is a gap between the upper limit of the previous class and the lower limit of the current class, because the upper limit is 69, the lower limit is 70 for the next class. Now, if at all I have a pulse rate of 69.5, where should I put? In this case, probably that kind of scenario does not exist. So, for that reason, this kind of intervals might have got created. But if I have to talk about the class boundary, it will include even the gap also. The gaps are also uniformly distributed between both the classes. Because the gap is 1 unit, both of them will share half of it. So the upper boundary will become 69.5 for the first class, and the lower boundary will become 69.5 for the next class. Instead of 70, limit can still be 70, but the boundary is 69.5. So when I have to represent the class boundaries, I will always represent them as 69.5 to 79.5, 79.5 to 89.5, and so on. That is what will constitute my class boundary. I should not leave any kind of a gap which are there as a part of the class limits. In some cases, if my limit itself does not contain any gaps, then my limit, there is no difference between a limit and a boundary. But in case of limits, if there are some kind of gaps between the upper limit of the first class and the lower limit of the next class, then obviously there is a difference between the limits and the boundaries as highlighted here. Then every class we also have a midpoint, which is nothing but just take the average of the limits, not the boundaries. Just take the average of the limits. So 60 plus 69 by 2 makes the midpoint of this class as 64.5. The next one 74.5, and so on. This the calculation of the midpoints will help us at a later point for doing some kind of calculations relating to the mean and all, which we'll discuss slightly later. But at this point, for every class we should also require the midpoints of the class, which are a simple average of the limits. Then when I talk about the class width, what is the size of the class? What is the width of the class? Sometimes the word is used also as size. What is the size of the class, or what is the width of the class? In terms of arriving at that, make sure that you are taking the difference between the two lower limits or two lower boundaries. Anything, both of them should give you the same value. You should not take the difference between the upper limit and the lower limit. Take the difference between either the two lower limits, 80 minus 70, 10. So across the board it is 10 only. Or even if I take it with respect to the boundaries also, it appears to be 10 itself. So in this example, the class width is 10. So these are some of the things which have to be considered while building a frequency distribution. So just coming back, I'll come. So how do we construct the frequency distribution? If we see, first there will be a data that would be given to us. Any data that is given, first determine the number of classes which we want to build. In this example, there are 7 classes. But every time you want to build one new frequency distribution, understand how many classes you would like to build. The ideal number should be between 5 and 20. And make sure that the number is a decent, comfortable number, right? Where the comparisons become more and more easier. The lesser the number of data elements you have, better to have lesser number of classes and vice versa. Then you calculate the class width. So here we have put the class width as 10. But how do I arrive at that? Let's say the minimum data for me is 65 and the maximum is 125 in the values. And I am thinking of creating 6 classes. Then the class width I would be computing as the maximum data value minus the minimum data value divided by the number of classes which I am thinking to build. So obviously it is coming out as 10. So the class width is coming out as 10. And now the next point for me is choose the minimum data value. See, first I need to decide what is my lower limit. To arrive at that lower limit, either I can choose 65 or I can very well choose 60. Either a value 65 directly, which is the minimum most value, or any comfortable rounded figure kind of a value, I can very well choose. Let's say I am choosing 65. Then what happens is 65, because the class width is 10, the lower limits of all the classes will be incremented by 10, something like this. 105 and 115. These would be the lower limits. And based on that, I can make upper limit. 65 to 74, 75 to 84, and so on. This will become my classes. Once the classes are identified, now take each data point, take each individual data value, and see to which particular group it will fall into. You have to make sure that every data falls only into one group. It cannot fall into two groups. Each of the original values should belong to exactly one class. You should not, let's say you have put it here as 75. The upper limit, let's say you are defining as 75. Nothing wrong. But you have to make sure if the pulse rate comes 75 exactly, where will you put? Will you put it as a part of the first class or in the second class? That clarity is very much required when we are defining the overlap, because one single data value should not go into two different classes at any point in time. And you have to include all the classes. Even if the frequency is 0 for one of the class, don't exclude that class. You have to include all the classes and maintain the uniform width. Though you can develop graphs with different widths, but it's always advisable to maintain a uniform width in the graph so that comparability becomes much more comfortable, right? So each element, each new data that comes in, you try to send it to one of the possible groups, and after all the data has been classified, that mechanism is called as a tally mark. You just put one tick mark to each of the group depending on to which group the data belongs to, for each element belongs to. And after all the elements have been allocated, just sum up, count the number of elements that are belonging to each of the groups and write it under the frequency column. That will bring out a table of this kind. So 60 to 69 there are 12, 70 to 79 there are 14. This is a simple mechanism that will help us in trying to understand in what range are maximum number of people lying. Probably just from this graph I can say 12 plus 24, 36 plus 11, 26 plus 11, 37 people are approximately having the pulse rates between 60 and 89. Only there is one odd case somewhere between 120 to 129, and hardly two people between 90 to 109, and there is no person between 110 and 119. So this will give us a broad level overview on what is the typical pulse rates among the people. So the data analysis becomes much easier when I look at a frequency distribution like this rather than a raw data. 40 items given comma separated may not give me a big picture, whereas if I am constructing a frequency distribution out of it and form a tabular statement like this, the big picture is clearly understood. So this is what about frequency distribution. So the first thing, whenever we have a large data set with us, it's better that we construct a frequency distribution. Now, how do we construct all these things? We'll take them up separately with Excel, right? But just understanding aspect of it, this is the procedure to construct a frequency distribution. And why do we use frequency distribution? Even if the data set is pretty large, we can summarize it quite comfortably. We can analyze the nature of the data, where the maximum values are lying, where the more concentration of the data is present, and that entire 5 characteristics of the data can easily be summarized once I plot a frequency distribution, once I develop a frequency distribution, and that forms the basis for constructing various graphs. We'll be seeing a later point in our chapter that will help us in constructing various graphs such as histograms and a lot of other set of graphs. Then along with the frequency distribution, people use another term called relative frequency, which is nothing but instead of expressing the frequency in absolute count numbers, like in this particular graph, in this particular table, the frequency is specified as 12 people, 14 people. So instead of expressing that in terms of absolute numbers, sometimes people express the frequency in a percentage form. That is what we call as relative frequency. Now in the earlier table 60 to 69 there were 12 people, but if I have to convert it into a percentage form, I am doing 12 divided by the total number of people that are there, which is the summation of that entire frequencies column there. 40 people are there altogether, and multiply it by 100, convert it into percentage, which will give me 30%. And that is what has been depicted here. So out of the total lot of people, 30% of them have pulse rates between 60 to 69. 35% of them have between 70 to 79, and so on. So even that will help us in doing a thorough analysis of what proportion of the total set of people have the pulse rates between X and Y. So because whatever is my data size, at the end the sum of all these things will be equal to 100% in relative frequency. So whatever is the size does not matter once I express once I express the frequency into a relative frequency kind of a model. So either I express it in a decimal form or a percentage form. Percentage becomes more and more comfortable in analyzing, because a simple addition of some of the numbers will tell me that these are the number of percentage of the people whose pulse rates are between this particular number and some other number. Alright, so we should be comfortable in evaluating the relative frequency distribution also, or constructing a relative frequency distribution from the original frequency distribution, and also the cumulative frequency distribution. Cumulative, as the definition is saying, it's a sum. It's a sum of the frequencies for that class and all the previous classes. Right? So if I have this data again, now the cumulative frequency for this class, the first class will be the normal frequency itself, but for the second class it becomes this class and all the previous classes sum. So 14 plus 12, 26 will be my cumulative frequency here. As far as this class is concerned, it becomes 37, because we keep adding up. Then one more is added in this class, 38, one more in this class, 39, 0 more in this class, 39, and this makes it 40. So by the time I reach the last class, it should be equal to my total frequency, right? And this also tells me how the values are increasing, where is a big increase in the values and where there is not, in which classes there is not much of a change in the value. And we'll see at a later point, we'll construct some kind of graphs called Ogive kind of a graph, which will take a cumulative frequency only into consideration rather than the relative frequency or absolute frequency. So in a frequency distribution, I need to know how to find out the cumulative frequency as well as relative frequency, because they have different uses in different contexts. We'll look at those things as we move along, but we have to be comfortable in creating these two aspects. Then one of the most important outcomes of looking at the frequency distribution or any kind of a graph is interpret the shape. Even if we see that one of the characteristics of the data is the distribution, and the most common distribution which we always keep talking about is the normal distribution, which we'll deal more and more about it as we move along. But as a quick summary of it, this is the distribution which is having a bell shape, right? Probably just to give an overview plot of it, there is a kind of a bell shape in it, The frequencies, if I think that these are the class intervals on the x-axis and frequencies on the y-axis, the frequencies start slow, start at a lower value, keep increasing up to certain extent, and then again decrease back to lower values. So this is the kind of a shape we call it as a normal distributed shape. It looks approximately symmetric, which means the left half should be a mirror image of the right half. So if at all, after I plot a graph of the frequency distribution, based on the frequency distribution, once I construct a graph, if I see that a similar kind of a shape is occurring with my data, then I call that kind of data to be more and more normally distributed. What are the three things I need to see? One, it should have a bell shape. Two, the values should, if it the values should be starting at a lower value, the frequencies should be lower at extreme values, and as the values are increasing, the frequencies keep increasing to a certain extent, and after that again they start falling gradually, and the graph is more or less symmetric in nature. The left half should be more or less a mirror reflection of the right half. In those cases, we call that particular graph to be more of normally distributed. So the most common graph that is constructed with the frequency distribution is the histogram, which is nothing but you convert the frequencies into vertical bars like this. If we see, the first one was having a frequency of 12. So I have plotted a 12 here. The second one a frequency of 14. The next one a frequency of 11. So just plot that data in the form of vertical bars. Some of the things to be kept in mind while creating a histogram: they have to have equal width, they should be drawn adjacent to each other, and no gaps. You see the picture here? Different ones are drawn with equal width. The width was 10, the class width was 10, and they are drawn adjacent, no gaps put. And what is that I am representing on the y-axis? On the y-axis it is the frequency, or sometimes people also use relative frequency here. Doesn't matter whether I use a frequency or a relative frequency. It really does not matter as far as the histogram is concerned. The graph will be more or less the same, only the scale will be different. The shape of the graph looks more or less the same whether I go for a relative frequency or a frequency. Whereas in the horizontal scale, we talk about the various data values. So in the data values, people will talk about either the class boundaries, as we are seeing here, the lower part of the class boundaries, or class midpoints could be there, or even the lower class limits. Any of them could be there, either the class boundaries or class midpoints or the lower class limits. Any of these things can be taken up. And on the y-axis, definitely it's a frequency or a relative frequency, and such kind of a graph that is constructed is what we call as a histogram. Again, in a histogram, at least I can see from the shape of this histogram that it is not normal in nature, because if it is normal, as we said, it should be a bell shape. The whole curve is not looking like a bell shaped curve, and there's no symmetricity anywhere in the curve, in the graph. So typically I cannot say that this is a normal distribution, which means it should be something else. We'll talk about what it could be as we move along, but at least it is not normal just by observing the simple histogram. Then in this chapter we'll also talk about various other forms of graph apart from the histogram, because graphs are excellent tools. A picture is much valuable than writing it in form of table or reports. So graphs are excellent tools for describing, exploring and comparing data. So from that standpoint, though we can talk about hundreds of graphs, in this particular chapter, I thought we should cover these particular types of graphs: a frequency polygon, an Ogive curve, then a dot plot, a stem plot, a bar graph, a Pareto chart, pie chart, scatter plot, and time series graph. So we'll have a basic understanding of each of these graphs. Then at a later point, we'll look at how do we construct these kind of graphs in our tool. Some tools give them automatically, and some tools we may have to construct some of the graphs in a slightly tedious manner. But whatever is the tool, as a statistician or a statistical analyst, our objective is to analyze the data or interpret the data just by looking at the graph. So we'll talk about these sets of graphs in this chapter, and any other charts and graphs that come to us at a later point, we'll take them up in those contexts. Now moving forward, frequency polygon. Instead of bars, vertical bars, which were represented as a part of the histogram, in a frequency polygon, I'll only plot points. If you remember, the first one was having a frequency of 12. So I have plotted a point corresponding to the midpoint. The class midpoints are what are plotted on the x-axis. Two things for us to understand here. Different class midpoints are plotted on the x-axis. Frequencies are taken on the y-axis. Any graph which we are taking, we should know what we take on the x-axis and what we take on the y-axis. Only then the entire comfort level will come in interpretation of the graph effectively. So I am taking the midpoints of each of the class on the x-axis and the corresponding frequencies on the y-axis, and whatever is the frequency of the class, I plot it corresponding to the mid value of that class. So corresponding to this 64.5, I plot a point. Then corresponding to 74.5, the frequency is 14, so I plot one here. Then the next class frequency is 11, I plot it here. And after that, it's a smooth straight line that joins all the points. So I keep joining all the points, and the first one will be joined back to the origin, and the last one will be joined back to the next. So it's like a closed curve. The next midpoint, let's say 134.5, if it has been continuing, the next midpoint should be 134.5. So the final graph would be, the final point would be joined to 134.5 with a frequency of 0, and the first point would be joined to the origin. So this kind of a graph, whether I take a frequency on the x-axis or a relative frequency on the y-axis or a relative frequency on the y-axis, it is immaterial. But the basic thing that has to be taken into consideration is all the points have to be joined by simple straight lines and joined back to the origin on one side and cutting the x-axis on the other side. This is what is a representation of a frequency polygon. Then we also talk about a typical Ogive curve. This Ogive curve, instead of frequencies, it takes cumulative frequencies. So basically like 12, 26, 37, 38, 39, 39 and 40. Just trying to remember the data which was taken earlier. So these were the cumulative frequencies of each of the classes. So then what I take is, I take class boundaries on the horizontal scale. I take class boundaries on the horizontal scale and the cumulative frequency on the vertical scale. So we had 60 to 69, so the first class boundary was 59.5, That is what I take as the origin value. Then 69.5, 79.5, those were the boundaries. And corresponding to each of the boundaries, we plot the cumulative frequency. So corresponding to 69.5, we take 12 and then 26 and then 37. So we just plot a straight line. It could be a straight line or it could be a smooth curve, whatever it is. But all we need to remember is the horizontal axis contains the class boundaries, the vertical axis contains the cumulative frequencies, and there's a line joining all of them. Why do we use this Ogive curve? Now, if I want to find out how many numbers are there below a particular value, so if I want to find out approximately how many people have a pulse rate below 75, okay, what I can simply do is 75 is somewhere here. So I take this line across parallelly, I take this line onto that Ogive curve, and wherever it intersects with the Ogive curve, I'll drop a perpendicular onto the y-axis, and I'll say approximately 20 people. This is an approximate. Approximately 20 people out of the 40, which is like 50% of the people approximately, have a pulse rate less than 75. So just to understand what is the total number or what is the total proportion falling below a particular value, we create an Ogive curve. So this is one more common curve which we use as a part of our statistical analysis. Then sometimes people also get into the dot plot. Very simple. All the possible values are taken on the x-axis like a number line. All the possible values are taken on the x-axis like a number line, and the frequencies are plotted as dots one above the other. So frequencies are plotted as dots one above the other, and they keep mounting up, they keep stacking up like this. So based on this, I can easily make out how many values are there in what region, or how is the data distributed, what is the centeredness, what is the distribution, what is the dispersion in the data. All these things can easily be understood just by observing the dot plot. So the plotting of this is very simple. There is nothing called y-axis in this, only a horizontal number line where different numbers are represented, and above each of the numbers, the frequency, each occurrence is represented as one additional dot. So probably in this example, for 40, there are 3, 4, 5, 6, 7, 8, 9 dots. What it means is the 40 must have occurred 9 times. 40 must have occurred 9 times. So what it is looking to us is at 40 the frequency is very high. Similarly at 25 the frequency is very high. Whereas probably at 50 the frequency is very, very low. Some kind of understanding can simply be made just by looking at this dot plot also. This is much more effective compared to many other charts. So sometimes just to bring in a variety in the presentation, people use this dot plots also. And then another common kind of a chart which is plotted is a stem and leaf chart. So what happens in a stem and leaf chart is each data is broken into two parts. Each data is broken into two parts, a left part and a right part. The right part typically contains the rightmost digit. Generally, the rightmost digit is the right part, and whatever is the left out in the data, with the complete leftmost part, is what is the stem. The rightmost is the leaf. Whatever, whether I take one digit, the rightmost one digit is the leaf, and leftmost whatever is left, because I'm breaking the data into two parts. Whatever is there to the right of the data, I call it as a leaf, and what to the left of that split, I call it as a stem. Now, each data is plotted like this. Once it is arranged in a serial order, in an ascending order. So, I take, let's say my numbers are 60, 60, 60, 64, 64. This is my data, let's say, after arranging it in an ascending order. What I'll do is, I'll split it into two halves. Not halves, two parts. Whatever to the right is what is called as a leaf. So there are 3 zeros in the leaf, 2 fours, and 6s are the stem. So as a part of the representation, what we'll do is we'll put the stem like this. 6, 7, 8, 9, 10, 11, 12 for our earlier data. I put the stems like this. And each leaf corresponding to this stem, I keep writing next to the other in an ascending order. So this means there are 3 60s, because 0 represents a 60 here. Here a 0 represents 80, because the stem is 8, leaf is 0, there is a value called 80. So I can easily understand there are 3 60s in the data, 4 64s and 5 68s in the data. So out of that 11, when we have done a frequency distribution, we were saying there are 12 people with between 60 to 69, but we don't know the actual values there. But in case of stem and leaf plot, I am writing all the actual values. So 6 is represented in the stem section, whereas in the leaf section I am writing 3 zeros, 4 fours and 5 eights, which is clearly saying there are 3 60s, 3 people with 64, 4 people with 64 pulse rate and 5 people with 68 pulse rate. Now, because of this, you just turn this by 90 degrees. You are seeing more or less the same impact of a histogram. If you had plotted the histogram, you see it's as good as 12 units. Then this is as 14 units and this is as 11. If you are just tilting the graph in this direction by 90 degrees, what you are seeing is the shape of the graph looks as good as a histogram itself. But the advantage here is we can retain all the information. In our frequency distribution, the actual data is not retained, only a summary is coming up. Whereas in a stem and leaf plot, the entire information is retained. So if I have to see, was there any issue with some of the data points, you can easily try to look at it and you can try to modify it also very comfortably. So the original data is not lost, but at the same time the summarization is happening. That's one great advantage you can derive using the stem and leaf plots. And at the same time, this is a quick way to sort the data. And as we move along, we'll see the data in a sorted order is very much required to find out some of the things like medians and quartiles. So this stem and leaf plot is a very quick way to sort the data also. And sometimes if the data is if there's a lot of data lying between 60 and 70 itself, I can expand it into two stems of 6 each, probably 60 to 65. I represent it as one stem and leaf, and 65 to 70 I can represent with another stem of 6. So sometimes I can expand it like that, or I can condense it. Even if I have 60 to 80, I can create a stem of 60 only, and then 86, 8 and so on, putting all the 20 values into the same stem also. So those kind of condensations or expansions can be done to make the stem and leaf plot represent the distribution of the data more effectively. So there's one more common graph that we need to look at from an interpretation standpoint. Then people also use bar graphs. One thing we have to understand, bar graph is more effective for a categorical data, not for the ratio scale kind of a data, or where there are intervals on the x-axis, where there are class intervals on the x-axis or class boundaries on the x-axis, then it is not effective. But if there is a categorical data like male and female, or such kind of categorical nominal or ordinal kind of a data, if it is there on the x-axis, and I have to represent the frequency or relative frequency or any such kind of stuff on the y-axis, then the bar graph is a very important graph. So the major difference between a bar graph and a histogram is, in the histogram we see that the x-axis contains the class intervals because it is more applicable for a quantitative data, whereas in a bar graph the x-axis contains the categories, the different values of a categories, so it is more and more applicable to a categorical data. So the horizontal scale represents the values of the categories, male, female kind of stuff, and the bars, the separation in histogram, it is mandatory not to have gaps, whereas in case of bar graph it depends on us, it is optional whether you want to create a gap between the graphs or you want to keep them close. This is not a criteria for a bar graph, and I can use multiple bar graphs like this. Now you are seeing in 1950 this is the income of males and this is the income of females. 1960 this is how it is. 1970 this is how it is. So this can help me in comparison. Probably the blue graph is growing up more like this, whereas the females one is not growing that much in the initial years, so it is falling more. It's not growing at a bigger rate compared to that of the male. Some kind of analysis can very well be done by observing these bar graphs over different points in time, but the x-axis typically represents categorical data. The y-axis is either frequencies or relative frequencies or any other calculation is what will result in the creation of the bar graph. One simple point to understand: the x-axis cannot be a scale or a quantitative data in case of a bar graph. If that is the case, it has to be represented only through a histogram. Then the same bar graph with a small deviation, instead of plotting it in any order, if I plot the same bar graph in the descending order of the frequencies, if the same bar graph is plotted in the descending order of the frequencies, the highest frequency one coming first and then the latest, then we call such kind of a graph as a Pareto chart. Especially if I want to draw more and more attention to only a few categories. What are the top 3 categories in the data? What are the top 3 categories? Top 1 category. Something if I want to highlight such kind of aspect, instead of searching through which is the one having the highest frequency and all, the moment I plot a Pareto chart, I can immediately see by what extent the highest one is differing from the next, because the next one, then the second one will always be adjacent to the first one, so comparisons become much easier. So the vertical axis can either be frequencies or relative frequencies, and horizontal is still a categorical different categorical values associated with the data. So it's the same as bar graph, the only difference being the bar graph is plotted in such a way in the descending order of the frequencies of various categories, not in the order of the original data, but in the descending order of the frequencies. Then the same bar graph information, if it is put in the form of a circle, and each part showing a slice of the circle, we call it as a pie chart. So there is no difference again between a bar chart and a Pareto chart or even a pie chart, because the Pareto chart also represents the various categories. Even a pie chart also represents various categories. The only difference is here the whole the entire set of categories are visualized as a circle, and the proportion corresponding to each category is mentioned as a proportion in the pie chart. So the size of each slice is proportional to the frequency. So that is where, from that standpoint, though Pareto and pi, both of them will give the same set of information, but they are presented in different formats. But what I personally feel is Pareto chart does a better job of showing the relative sizes in different way, because both these graphs are more or less one and the same of the same data. What I could clearly see is I can very well see the relative size differences in case of Pareto chart very easily, whereas in some cases it may be difficult quickly making out between green, blue and orange which of these three is greater compared to the other. A quick visual inspection is not that easily possible, or even if I look at these two, which of these two is bigger. A quick impression cannot come out using a pie chart, especially if the values are close by. Whereas in case of Pareto chart, everything is clearly evident, whether any two particular categories are same in frequency or something is slightly better compared to the other. So the presentation is more comfortable in case of a Pareto chart compared to a pie chart. So, but we need to understand even the creation of the pie chart, because sometimes for making effective presentation, bringing in a variety in the presentations, all these things can definitely be of help for us. Then, if I am taking two quantitative variables and want to analyze them together by taking one variable on the x-axis and the other variable on the y-axis and plot a graph, I call such kind of a graph as a scatter plot. So it helps for me. What is the benefit of having a scatter plot? It helps me in deciding whether there is any relationship between x and y, which means as x is increasing, do I see a pattern in the value of y increasing or decreasing or no change? Similarly, if y is increasing, is there any pattern with respect to x? Is x also increasing by the same amount, or x not increasing at all, or is x decreasing? So such kind of relationship between x and y values can very well be visualized using a scatter plot. We'll discuss at length of the scatter plot when we take up correlation and regression as the chapters. But for the time being, just a basic understanding of this chart says I need to talk about two quantitative variables together, because till now, whether we did a frequency histograms or polygons or for that matter bar charts, only one variable, only frequency was taken on the y-axis, frequency or relative frequency or any of these things, and x-axis was merely either a class interval or a class boundary or a category, but it's not actually a value. So in case of scatter plot, that becomes a value. X-axis also has some values, y-axis also has some values. They are not mere representation of the classes or categories. In that case, we refer to the using of scatter plot. So the prime advantage of doing a scatter plot is finding out the relationship between x and y variables. If x is growing, is y also growing or falling or remaining constant? Then we also have a time series graph where the x-axis is clearly a time based, years, months. So the time related, date related data should be there on the x-axis and any value on the y-axis. So if I am tracking the values corresponding to various points in time, the same value if I am tracking over different points in time and try to plot a graph. So the major thing is x-axis should be a time and y-axis can be any value corresponding to that time. If I try to plot a graph between those two, I call that graph to be a time series graph, and that kind of data I call it as a time series data. So it should be a quantitative data collected over different points in time. Here we are saying 1980 to 2005. Some kind of values plotted and joined as a line. This particular graph is what we call as the time series graph. So these are the different kinds of graphs that we have to, we keep building very basic graphs. Of course, there are hundreds of other graphs that are possible also. But as a basic introduction to the world of graphs, these are the graphs we need to be comfortable with, because they help us in broadly analyzing the data at a higher level. Some of the points that we need to remember while constructing a graph: if my data set is very small, having only 20 or lesser values, it is suggested to use a frequency distribution table rather than a graph, because graph may not bring out sufficient understanding. Only if the values are large in number, if the data set is large in number, and there can be a significant size to the graph, then only the interpretation becomes more and more handy. Otherwise, there is no point in representing a graph. It's better to use the table itself. So any kind of graph you are plotting, we have discussed 9 to 10 varieties of graphs. Any kind of graph you are plotting, the focus should be on the true nature of the data, not on distracting design features like, should I make it three-dimensional? Should I put 100 different colors? Should I put different patterns in the graph? They make distracting. Any eye-catching feature is good, but distracting feature is bad. And just for the purpose of creating a good graph, don't distort the data. Let the graph reveal the true nature of the data. And don't use three-dimensionals or slantings, because sometimes illusions could be created, and the actual data analysis will become more and more problematic. And suggested to use two-dimensional graphs unless the representation requires an area or a volume kind of stuff. Don't represent areas and volume kind of graphs, a cubes or a cylinders kind of graph, in order to represent a one-dimensional data. To represent a one-dimensional data like values, like the heights, weights, which are of a unidimensional, or the size, instead of representing a three-dimensional graph, better represent a two-dimensional graph, which will be clear in terms of presentation, rather than going for area or volume kind of graph. And if you are going from a print standpoint, never publish the pie chart, because a lot of thing goes only in terms of colors and highlightings, rather than any particular value getting more attention. Because every pie chart, the whole pie is filled with one single color, or the whole slice is filled with one single color, though you can manage it with some simple understanding on that. But focus is not majorly on the data there, it's more on the distracting design feature. So from that standpoint, it is suggested that especially when you are going for a print or a publishing, never try to use pie charts, either a Pareto or a bar. These kind of charts will definitely cover the entire intent of a pie chart. And people also talk about bad graphs, right? Though on one side we are constructing good effective graphs, but we should also know what a bad graph is. One, it contains errors, means I did not use the appropriate graph, then I call it as a bad graph. But technically it may be correct, but misleading. Sometimes like this, there are two major things that can come up: a non-zero x-axis or a y-axis. Here, if we see, I am taking the base to be 53. If the base is taken as 53, then probably 62 is looking as if there is a big difference. Just as a graph, if I am seeing that there is a huge difference between 62 to 54. So just as a visual inspection, it will tell me that there is a huge difference. But probably if I had taken 0 on the y-axis to start with at the bottom, probably the distance between 62 and 54 would have been negligible. So just to show big differences, if I try to make this much of differentiation in the axis, it becomes completely misleading. So you have to make sure that you are going with zero based axis only, both on the x as well as y. Otherwise we get into this kind of misleading results. So one thing we have to be careful of, because people won't look at what is there on the x axis and y axis. They just visualize the graph, just look at the visual representation of the graph and try to take some conclusion. So we have to be very careful with the non-zero axis, or sometimes the pictorial graphs. Alright, a pictorial graph, simply if we see, if I put a three-dimensional data like a cube to represent these two things, right, or probably the second and the third, I want to show that this value, the third value is almost double to that of the second. So if I try to increase the length, width and the height, both of them by 2, the actual area is not increased by 2. The cube is looking much bigger compared to a simple line or a rectangle. Because what is happening in that process is, I am increasing the length, width, height, everything by 2, which actually increases by the volume of this graph by 8 units, but not double. So what happens is, a three-dimensional graph, especially which represents a volume kind of stuff, it magnifies. Actually, I need to see that the impact is just double. I need to know that from here to here there is a double in the number. But because of using a three-dimensional, I'll get either this particular box is 4 times to this box, or at least 8 times to this box. So because of that, it creates an illusion again. So especially the usage of three-dimensional graphs or pictorials kind of graphs, some cylinders, some persons, especially if we are representing these kind of things for unidimensional data, we have to be very careful of, because analysts they get distracted by looking at these things, and the interpretation may go slightly wronger. Probably if we see the last one, third and fourth, there is not even 1.5 times between the third and the fourth. But what we are able to see from the graph is the fourth one is looking much bigger compared to the third. Right. So plotting it as a three-dimensional graph will lead to this misleading. So these are typically what we call them as bad graphs. Don't put a non-zero axis, which will mislead the results, and don't use the three-dimensional or pictorial graphs, especially if you have to represent a unidimensional kind of a data. Yeah. Any further questions on this? We can very well discuss them out. Even at a later point also, if you are finding any queries regarding the different forms of summarizing the data, either in the mode of frequency distribution or relative frequency distribution or cumulative frequencies, or painting different kinds of graphs, histograms, polygons, dot plot, stem and leaf plots, Ogive curve, or bar chart, Pareto chart, pie chart, time series chart, scatter plot, any of these things, if you are having any further queries or clarifications on this, you can feel free to contact me on the number that is displayed below, 9848012123. You can even mail me at vamsidhar@pacegurus.com. I request you to visit my website www.pacegurus.com for any further queries regarding the further courses in the area of finance, analytics and statistics, using tools like Excel, SPSS and VBA. Thanks a lot for listening to this session. Thank you very much.